Once the capacitor is fully charged, we call it steady state. And then it completely blocks the current. The resistor will get no current when the capacitor is completely charged. There is no way for electrons to travel between the two plates. I'm talking about ideal situation when capacitor does not have any leakage current taking place. This could be a very simple drawing, just showing one capacitor, one resistor and one battery. But even when you have a large network and there are several resistors, several batteries, several capacitors, you can always find loops, and at steady state all the capacitors that are present will completely block the current. Only when charging is taking place, only that time you can say that current is flowing. You can say that sort of a current is flowing when charging is going on. And charging goes on for a very short period of time. We will be doing transient state analysis also for capacitors, and when we do transient state analysis, then we look at the time. How much time does it take for capacitor to build this much charge, etc. Capacitor does not build charge instantly. It's not like you switch on the battery and capacitor is fully charged. Not like that. As and when capacitor gains more and more charge, it opposes the battery more and more. Positive terminal and positive terminal are not going to make good friends. Two batteries support each other if plus of one faces minus of the other. So even if when the charge is building on the capacitor gradually, it is opposing the battery, right? And when capacitor is fully charged, it blocks current. So at steady state, the capacitor acts like an open circuit. It's like you have cut that part and no current can flow through that part. When you deal with problems which involve this type of analysis, it really is very easy. It really is very easy because you can simply cut those regions where capacitors are connected. So look at these problems. Let me put up the first one. Now this question says find the charge on the capacitor at steady state. Right, so this is about steady state analysis. And by the way, in the topic on capacitors, we were dealing with primarily steady state analysis. Transient analysis will be covered in this topic, and that is something which we will discuss later on. Now, regarding this steady state analysis, capacitor has been charged and it blocked the current completely. Cut it. It's an open circuit. So, just imagine it's not there for a moment. So, current will flow like this. And that means current would be 2 by 30 amperes. We want charge. We want charge on the capacitor at steady state. Once you know current, what would be the potential difference across these 2 points? 10 times 2 by 30, which is 2 by 3 volts. Now can you try to tell the answer? If 2 by 3 volt is the potential difference across these 2 points, 2 by 3 should be the potential difference across these points. Now I have cut because there is no current flowing, but actually it is in contact. So this potential is same as this potential. This potential is same as this. So if it is 2 by 3 here, it must be 2 by 3 here also. You know the potential difference, you know the capacitance, it should be possible to tell the charge. Alright, let me complete it. Yes, the unit that you are using is coulomb or 4 microcoulomb. We want VA minus VB and VB minus VC at steady state. When it is steady state, as far as current is concerned, you can cut this. Well, looks like there is going to be no path for the current. Look at it. From where can the current go? Everywhere there is a dead end. There will be no current at steady state here. Now supposing we call point C as our reference point. Reference point means say 0 volt. Then can you tell me what would be the potential at A? No current is flowing, so this resistor cannot create any drop. This resistor cannot create any drop. Whatever is the EMF, that's it. Left side is 200 volt, or rather, I think this should be 100. Left point is 200 volt, 100 volt. Left point is 100 volt higher potential than the right point. Right point is 0 potential. That means A is going to be at 100 volt. All these points are at 100, 100, 100, 100, 100, 100. I have done redrawing so that things look somewhat clearer. They're all at the same potential. Now that's why I have shown this point as A. Then this 3 and this 3 are connected across the same 2 points. This point B, and this is A, this is all A. So actually these two are connected across A and B. So they are in parallel. 3 plus 3 is equal to 6. Then this is B, this is B. This is C, this is C. So if you look at these two fellows, they are connected across B and C. 1 plus 1 equal to 2. then this 1 microfarad is connected across A, this is all A, and C, this is all C. So it is 1 across A and C. Once you get this drawing, I think things should look really easy. If you have any questions up to this point, let me know, or I will proceed further. Looks like we can move on. C is at 0 potential, 0 volts. When you have two capacitors in series, then we have a direct result to find potential difference across any one. So VAB, which is same as V6 microfarad, that would be depending on the other capacitors upon C1 plus C2 multiplied by 100. So 2 by 8, 1 by 4, 25 volt. 25 volt should be the potential difference. So if this is 100, this should be 75. And VB minus VC is obviously 75 minus 0. Now there may be a switch that I have not shown. Imagine this circuit is there and capacitor is not charged initially, and you connect the switch. Capacitor will get charged. As current flows, positive charges will be deposited here. In other words, technically more correct, electrons will be moving like this. Electrons will be moving away from this plate. So positive charge will be coming here. And negative plate repelling negative electrons, so electrons will be accumulating here. Whatever way you like to think, plus here, minus here. But it's not instantaneous. Electrons have to travel. And when electrons travel and some positive charge comes, then it makes it more difficult to more electrons to travel. Because now positive charge will somehow attract those electrons. Yes, this may be more mighty in pulling electrons, but still opposition is there even if it is slight. But then that opposition will become larger and larger as more electrons go away and away and away. It becomes more positive, more positive, more positive. So one stage comes when electrons are just not able to move like this. That's it. Capacitor is completely charged. Whatever we have been doing till now, mostly or almost completely is a steady state type of situation. But now we are going to see when the charging is going on, when the build-up of charges is going on, that is the transient analysis, then what are the different parameters that we can have? What are the different parameters that we can have? So that is the transient state analysis. There are two things in transient state analysis or transient analysis. One is the charging of capacitor and the other one is the discharging of capacitor. Right now you are seeing charging of capacitor. Now, let's say at any instant t. Now first of all, at t equal to 0, switch is connected. At t equal to 0, switch is connected, right? And at that instant, the capacitor had no charge at t equal to 0. At t equal to t, let's say some charge built up has taken place, plus q on the left and obviously minus q on the right. But it is changing, small q is changing, so it's not a constant. Eventually it will become a constant. So you can call some current. Some current is actually flowing, you can say, think like that. Now we can apply Kirchhoff's law if current is flowing. So let's walk from this point going clockwise. So minus to plus, we are going from lower potential. Minus E. Then we are going from positive plate to negative plate. This is positive, so plus q by C, and then we are going like this. Current is entering, so this must be the plus side, so it must be plus IR equal to 0, and Q is going to increase. That's very important. I can be sometimes plus dq by dt, sometimes it can be minus dq by dt. In the current context, Q will increase and direction of I has to be this. So dq will be positive if Q is increasing. Change in Q is positive if Q is increasing. Change in time will be certainly positive. So it will be plus dq by dt. You have to be careful as we discuss more things in future, plus dq by dt, minus dq by dt thing. Now we are able to get a differential equation, minus E plus q by C plus R dq by dt equal to 0. Separate the variables. This is not a challenging differential equation. It is very easy to separate variables here. So we have R times dq by dt equal to E minus q by C. So we have R dq upon E minus q by C equal to dt. So simply they are separated. At t equal to 0, when we press the switch, Q was 0. Now you may face certain problems where capacitor is not charged at t equal to 0. So don't use the formula which we are going to get in those cases. You will have to go by basic approach in those problems, just like we did from the very beginning and looking at the integration limits. So understanding derivation is very important. 0 is what we are assuming as the initial charge in capacitor. When T is 0, Q is 0. At an instant T, charge is Q. Capital R is constant. Integral 1 upon E minus Q by C. Minus 1 by C. This goes from 0 to Q. That is T. So minus RC, putting the limits, E minus Q by C minus log E. That is T. I just copied that last thing from the previous board to this board. And let me drag it up. Okay. So we have now taking anti-log T to the power minus T by RC. Splitting the left side, e to the power minus T by RC. This is CE. Well, that's the final result, you can say. Now, if you find that instead of E it is some voltage V, you can use that V. That's the same thing. E is what basically? E is the potential difference across these 2 points, this and this. That's E. If you read it, understand it, e to the power minus x function, you know how that function behaves. It's a falling function. E to the power minus x is a falling function, monotonically decreasing, strictly decreasing function. That means as time goes by, this number becomes smaller and smaller and smaller. And therefore, 1 minus that becomes larger and larger and larger. And therefore, now C into E is a constant. C into E is multiplied by something which is becoming larger and larger and larger. So obviously Q is becoming larger and larger and larger. If you want the limiting value or the maximum value of Q, take the limit t tending to infinity. When you take the limit t tending to infinity, that thing is gone. and the charge eventually is going to be CE. That's the maximum charge, and while theoretically it may look infinity, theoretically infinity is not like practical infinity. Practically does not mean that you have to wait till the end of the world for that capacitor to get fully charged. Infinity is always a relative thing, practically speaking. And what you find practically is that it does not take long time to charge a capacitor fully by following this procedure. So actually, while in theory it looks like t tending to infinity, in practice this time is very, very short, and in that short period of time capacitor gets fully charged. Now once it is fully charged, the story no longer belongs to transient state analysis. Now the story becomes that of steady state analysis. Now capacitor blocks the current completely. Current becomes zero when capacitor is fully charged. So we say that at steady state, a capacitor is an open circuit. It blocks current completely. But see what happens at t equal to 0. See what happens at t equal to 0. Let's talk about current. We have talked about charge. Let's talk about current also. So charge build-up is given by CE I have written the rest of the things, and by the way, if you like, in place of CE, you can call it Q infinity, the final charge. Now I was talking about current. Current is dq by dt in this particular context. That means when we differentiate, Q infinity is a constant. Q infinity and e to the power minus t by RC, and RC will also come here. Let me write CE back because I can see something interesting coming up. If we do that, and that interesting thing is E by R. Now, again, e to the power minus x type of behavior is a falling behavior, so E by R is fixed. E by R is multiplied by something which is becoming smaller and smaller and smaller. So that means current will become smaller and smaller and smaller. And if you take t tending to infinity, then current is zero. That's no surprise. When capacitor is fully charged, it will block the current completely, no current. But when you put t equal to 0, you get another interesting result. When you put t equal to 0, you get I equal to E by R. That's a very interesting result. Look at this circuit. Now, if I is E by R, what does it mean? It means circuit does not see capacitor there. Ohm's law is working directly, I equal to E by R. You don't apply Ohm's law normally when you have capacitors. It's as if C is not there. As if in place of C it were a straight wire. That's how Ohm's law is working, I equal to E by R. So the conclusion is that the capacitor behaves as short circuit at t equal to 0. Short circuit means you have two plates. Imagine two plates are connected by a nice conducting wire, straight. That's the meaning of short circuit. You have 2 points, you connect those 2 points by a nice conductor. That's the meaning of short circuit. So capacitor is short circuit at t equal to 0. It allows current to flow very nicely. Opposes no resistance to current, capacitor, initially. But as charge builds up on it, it opposes more and more and more, and eventually makes current kneel down and become 0. Right? So please remember short circuit and open circuit. T equal to 0 short, T equal to infinity open. In physics, you cannot have a physical quantity which is whatever it is, Q or X or whatever it is, which is equal to some number 2 to the power . Let me put it in these words. You can never have 2 to the power some dimension type of thing. It doesn't make any sense. Now, dimension can never come in this position in physical quantities. Look at this particular case. E is a number. E is 2.7 something. Now, 2.7 to the power dimension is not allowed. That means T by RC must have no dimension. But T is time, and you want no dimension. You can check R into C. If you like, you can check. But from simple argument, you should be able to say that because totally this cannot have any dimension, and therefore RC should have the same dimension as T. It can be verified also by putting the dimensional formula for R, by putting the dimensional formula for C, multiplying the two. So RC is time, and RC is called time constant. RC is called time constant. And we denote it by tau. How is the behavior of Q? Broadly we discussed how is the behavior. It's a rising behavior and then saturating. It does not continue to rise till infinity, but it saturates at some value eventually. So we know that behavior. But graphically, how is the behavior of Q, and what is the significance of time constant, tau? Well, you know the graph of e to the power x, e to the power minus x. There has to be synergy, some synergy to that. And it is somewhat like this. So rising and then saturating, that's it, fixed. And that fixed is Q infinity or EC. Q infinity or EC. What is the significance of time constant? If you put t equal to tau, then you find that at that time tau, q becomes q max 1 minus 1 upon e. And when you calculate that, you find that it becomes 63%. Q becomes 63% of its max value. It becomes 63% of its maximum value. That's the significance of time constant. So you can see in one time constant itself, it has reached 63% of its maximum value. And time constant is equal to RC. I was telling you practically it's a small time. You know that capacitors normally have small values, 10 to the power minus 6, 10 to the power minus 9, etc. So if you consider 10 to the power minus 6 here, and if you take a resistance of say 1000 ohms, 10 to the power minus 6 into 1000, you get 1 millisecond. Just 1 millisecond time, and the charge becomes 63% of its maximum value. So that's why I was saying that practically charging is a quick process, even though mathematically we say limit t tending to infinity. It's as simple as that. Just calculate that. You should mention the unit. I suppose it is second that you are saying. And the answer I have is .18 microseconds. Just check for a factor of 10. I think we move on. Electric field inside the capacitor. Now that E and this E, let me use this E. This is the field E. If potential difference is V and distance between the plates is D, then this is how you can find electric field. Electric field depends on the potential difference, and C is Q by V. V across the plates depends on C. So battery's EMF is different. The potential difference across the capacitor plates is different, which we are calling as V. And because of the potential difference across capacitor plates, there is electric field, which we are calling as E. As Q changes, V changes. And E changes. Find the electric field 10 nanoseconds after connections are made. That's no problem at all. Q upon CD. Plate area is given to you. D is given to you. The only thing is Q. And Q is found by, this is a charging case, Q is found by Q maximum Q maximum 1 minus e to the power minus t by tau or RC. EMF you know, 2 volt, D you know, resistor you know, capacitance is epsilon naught A by D, area you know, distance you know. Calculation I am leaving up to you to do. This is not assignment, but you should do it to confirm that you are getting this answer. So when I say not an assignment means submission is not required, and the answer is 1.7 into 10 to the power minus 4 volt per meter. (1.7 into 10 to the power minus 4 volt per meter). Any questions? If you have, then let me know right now. Fine. We stop at this point.